Are you able to see my screen? Oh, okay, so I'll make it full screen. So can you see the screen? Oh,
Yes, sir.
okay. Okay, so in the last class we reached up to here, okay? So dealing with equality constraint. So we saw that if you have a constraint like this, it is difficult to separate the variables. Okay, you cannot take x to one side or y to one side or z to one side. So there you need to have a general method. So that is this Lagrange's method. So basic of Lagrange multipliers. First is necessary condition for equality constraint problem. So suppose you have to minimize an objective function f of xy, and there is also an equality constraint hxy is equal to 0. Okay. So if x star y star is the optima, then it must lie on the equality constraint h of xy is equal to 0. Or in other words, h of x star y star is equal to 0. And also you know that okay, so it's not unconstrained problem. Okay, so this is the condition. Okay, so the point must lie on the equality constraint, and h of x star y star should be equal to 0. And what is the value of this x star y star? Okay, so the method used it. We use the Taylor series expansion. So consider two small quantities dx and dy close to the optima. So some contours are like this. Okay, so this is h of x star y star. Okay, so we take 2 points close to this h of x star y star. Okay, maybe a point here. Okay, so this is x star plus dx, y star plus dy. Okay, so this point is close to this line, so that will also tend to 0. So it can be shown from the Taylor series expansion up to the first derivatives, or the second derivatives is ignored. Can be shown from the Taylor series expansion. I am showing only the final result. Okay, then the following condition is got from this Taylor series expansion. That is partial f by partial x minus nu into partial h by partial x equal to 0, and then partial f by partial y minus nu into partial h by partial y is equal to 0, where nu is equal to df by dx. So there is a long derivation which I have skipped. I am showing only the final results. Okay. So long derivation of Taylor series in two variables x, y has been skipped, and only the final result is shown. Okay, so this is the necessary condition for the optima of a equality constraint problem. Okay, and this ratio and this factor df by dh is actually the rate of change of objective function for unit change in the constraint. So that is the meaning of df by dh. Okay, so that will later become Lagrange multiplier. Okay, the same equation can be obtained by using the Lagrange function. So even without using any Taylor series expansion and all, we can get this same equation by using Lagrange function. Okay, so what is Lagrange function? So suppose I want to minimize this f of xy subject to this equality constraint. That is h of xy is equal to 0. So the same problem I write like this. Okay, that is, and this function is called Lagrangian. Okay, this is called Lagrangian. That is L of xy nu. So L of xy nu is equal to f of xy minus nu into h of xy. So this problem is written like this. Okay, it's written like this. Okay, so what happens is that this equality constraint, which used to be a separate statement, is now inserted into the objective function. So it becomes unconstrained function because the constraint is absorbed into the objective function. So this is called the Lagrangian function, and nu is the Lagrange multiplier. Okay, so now if you okay, so this is the Lagrangian. I've written it again. Now if you do this del of L is equal to 0, we get all the equations we got from the Taylor series function in the previous slide. So partial L by partial x will give this is equal to 0. Partial L by partial y will give this is equal to 0. And the partial L by partial nu will give that is h of xy is equal to 0. So these are the necessary conditions to satisfy the minima of the equality constraint problem. Okay. So if you solve these three equations, you can get x star, y star, and also you can get the value of nu star. X star, y star is our solution. Okay. Okay. So the value of nu star is not it's not very important for equality constraints, but for inequality constraint problem later, this value of nu star will give the direction in which the contours of the objective function are approaching the constraint. So the value of nu star or the sign of nu star is important for inequality constraints. Okay. So if you have equality constraint like this, it doesn't matter if the contours are coming from here or contours are coming from here, as long as the points are on the equality constraint. But if you have inequality constraint like this, okay, so this will give the minimum, of the inequality constraint problem if the objective function is outside the feasible region. If the objective function is inside, then it becomes inactive constraint and there's no need for this constraint. So this is actually the minimum. So that direction is given by nu for inequality constraint problem. So that we'll see later. Okay. Okay, now suppose you have three variables, x, y, z, and many equality constraints. So then we can write the Lagrangian in this form. Okay, so f of x, y, z minus nu1 h1, nu2 h2, nu3 h3. Then this del L is equal to 0 will give 6 equations. That is partial L by partial x equal to 0, partial L by partial y equal to 0, partial L by partial z equal to 0, partial L by partial nu1 equal to 0. So 6 equations will come, and you can solve these 6 values, and x, y, z star is our solution. So we look at some worked out examples of this. So minimize this objective function, and this is the one and only equality constraint. So h of x is equal to 0. So what you do is you write it in the Lagrangian form. Okay, so f of xy minus nu of h of xy, and you can substitute all the values here. X squared plus y squared is f of xy, and h of xy is this term. H of xy is this term. Okay, so now you can put partial L by del, this first derivative with respect to L is equal to 0. The partial x by partial L by partial x equal to 0 will give this equation. Partial L by partial y equal to 0 gives this equation. Partial L by partial nu is equal to 0 gives this equation. So you have 3 equations, 3 unknown. Okay. Okay. And you can solve the value x star equal to 4 by 5, y star equal to 2 by 5, nu star equal to 4 by 5. So you got your answer, x star and y star. And for equality constant problem, the value of nu star is not very important. It only shows that the contours are approaching from which direction of the constraint boundary. Okay.
Professor sir, I have a question, sir. I'm sorry to interrupt.
Okay.
Sir, Professor sir, this equality constraint is 2x plus y minus 2 is equal to 0.
No.
In this, x and y are explicit, like we can express x in terms of y.
Yeah,
So
yeah.
probably here, if we want to solve it in a traditional method, like if we replace y is equal to
That you can do.
that
Yeah,
also,
also.
sir.
But in this method, advantage that you are doing this partial L by partial x equal to 0, partial L by partial L y equal to 0, you get more manageable equations.
Okay.
Okay. Huh?
Right.
Whereas in the earlier method, you had to use your intelligence to express y in terms of x and do all manipulations by yourself. I mean, without a standard method. Here you get standard set of equations like this. This is suitable for automatic solution. Okay. So some equality constraint problem you can do like what you said. You can replace the variable and do that, but not all. Okay. So this matrix is much more easy to solve than the substitution method. Also, when you take partial L by partial x equal to 0, partial L by partial y equal to 0, some higher terms will go away. For example, 2x squared will become 4x when you take the derivative. The terms will become simpler. Okay. Okay, then we look at another example. A boiler has 40 tubes and has to be corrosion coated. The length of each tube is L and diameter is D. So length of each tube is L and diameter is D. Okay, diameter is D. And 40 tubes are needed. Okay, so 40 is fixed. Okay, and L and D are the variables. You can change the value of L and D. Okay, so that is the optimization variables. So then the total cost which has to be minimized is C1 plus C2 plus C3. So C1 is like this. 40L D raised to 2.5. C2 is 950. Some fixed cost, maybe some material cost. Then C3 is equal to 40L into D. 40L into D means the painting of the outer surface, that type of surface area. So this is the total cost has to be minimized. Okay. And so this is the objective function. Minimize C1 plus C2 plus C3. And one equality constraint is given. That is the total core volume of all tubes must be exactly 450 units. Okay. Or the cubic capacity of all the tubes must be like 450 cc or something. So this is the equality constraint. H of LD is the equality constraint. So you have to minimize this objective function subject to this H of LD is equal to 0. So that we'll do in the usual way. So this is the objective function subject to this equality constraint, and equality constraint is simplified like this. Okay, so it is further simplified like this. Okay, so now we can write the Lagrangian equation. So this is the objective function. Actually, this should be 950. objective function minus nu into h of LD. Okay. So we write like this. Okay. Then partial L, capital L by partial small l will give this equation. Then partial capital L by partial small d will give this equation. Then partial L by partial nu will give this equation. So you can solve these three equations. If you want, you can make a substitution. So from this equation, you can put L equal to 45 by pi d squared in these equations. Okay. So wherever you see L, you put 45 by pi d squared. Pi d squared. Okay. So then you will get two nonlinear equations, okay, in L and D. So that you can solve by some MATLAB method. A lot of nonlinear methods of solving equations are there. So if you give there, if you call that MATLAB subroutine, you can solve for L and D. Otherwise, you can give the entire set also to the MATLAB solver and it will solve. Okay. And finally, you will get 5.6. A length should be 5.68 meters. D star should be 1.59 and nu star should be 191.11. Okay, you have to check these values. Okay, this is a meter or millimeter, so no, you have to check these values. But these are the right values of L and D. Okay, so this is the way you solve this. You solve equality constraints with the Lagrange method. But the difficulty is not in solving equality constraint, but in solving inequality constraint. Because equality constraint, you know that the final solution has to satisfy h of xy. So starting point of the solution is known for equality constraint. Okay. So how do you solve inequality constraint? So that is the difficult task. Okay. So there is a certain type of conditions called KKT conditions. So this is called Karush-Khan-Tucker conditions. So these are the people who first wrote the paper on how to solve inequality constraint using Lagrange method. Okay. So inequality constraint can be active or inactive. It is usually not possible to predict in advance if a constraint is active or inactive. And switching conditions can be used to check if a constraint is active or inactive. If it is active, it is solved as an equality constraint because solution will lie on the boundary of the problem. If not, constraint is ignored. Okay, so suppose you have contours of contours of objective function like this. This is your inequality constraint. This is the feasible region. Okay. So this is a active constraint. So to solve this problem, you only need to solve the equation of the constraint boundary and the equation of the objective function. So it is become like equality constraint. Okay. So this is if the constraint is like this. So now let's take another case. Okay, so this is the contours of the objective function. Feasible region of the constraint is coming like this. Okay, so this constraint is inactive. Okay, it's inactive because we can ignore this constraint and we can directly find this minima by equating the first derivative of the objective function to 0. So the switching conditions will tell you whether it is this case or whether it is this case. So if it is this first case, you only need to solve the equation of the constraint boundary and the objective function, and you will get your x star y star here on the boundary of the objective function. And if it is inactive, the switching condition says that constraint is inactive, you can ignore the constraint, you can just directly differentiate the objective function and you can find x star y star. Okay. So this is the problem faced by inequality constraint, which is not faced by equality constraint. Okay. So solving this Lagrange function problem for inequality constraint with slack variables. So first of all, the inequality must be written in the less than or equal to 0 form. So suppose it is x plus y is greater than 2, we have to write minus x minus y is less than or equal to less than or equal to 2. Oh no, you have to write it in the less than or equal to 0 form. Minus x minus y plus 2 less than or equal to 0. Okay. So you have to write it in this form. Okay. Then we make it into an equality constraint by adding a slack variable s1 squared. Okay. So s1 squared is a slack variable, meaning that its value is either positive or 0. That is the meaning of slack variable. So now let us look at this expression. Okay, g1x plus s1 squared is equal to 0. So negative value of s1 squared means g1x is positive, which will violate this constraint. Okay, so suppose s1 squared is equal to minus 2. So that itself is wrong, because s1 squared square of a number cannot be equal to minus 2. So g1x minus 2 is equal to 0. So g1x is equal to 2. So that means it is violating the constraint. Okay, because g1x has to be less than or equal to 0. So the negative value of s1 squared means g1x is positive and the point is in the infeasible region. So that is one switching condition. Okay. Then if s1 squared is equal to 0, it means that g1x is equal to 0. So it is lying on the boundary of the g1x constraint. So it means active constraint. Okay. So if s1 squared equal to 0, it means active constraint. Okay. And now suppose s1 squared is greater than or equal to 0, then g1x will be negative and the point will lie inside the feasible region, so it is inactive constraint. So this is the switching conditions. Okay, switching conditions are s1 squared equal to 0, s1 squared equal to plus, s1 squared equal to negative. Okay, so this means active constraint. This means inactive. This means infeasible. Okay. So we can check the value of s1 squared and arrive at either of these three conditions. Okay, so what we do is that we write this Lagrange equation like this. So this is the previous form of the equality constraint. So minus u1 into the g1x plus s1 squared. So now this is inequality. I mean, now this is equal. Now this is like an equality constraint. Okay, an equality constraint. Okay. So we can use the same approach as the equality constraint which we used in the previous slides. Then instead of the term new one, we use u1 for inequality constraint. So this new one is for equality constraints. Okay. So we use the term u1 for inequality constraint. So then you can put this del of L is equal to 0. We get partial L by partial x equal to 0, partial L by partial u1 equal to 0, partial L by partial s1 is equal to 0. All three equations are got, and we can find the value of x, u1 and s1. All these values can be found out. Okay, so now let us look closely at this, partial L by partial s1 is equal to 0. Okay, so this is the term, s1 squared term. So partial L by partial s1 of s1 squared. That is 2. Okay, this u1 has to be multiplied here, u into s1 squared. So 2 u1 s1 is equal to 0. So this is called switching condition. u1 s1 equal to 0 is called switching condition. Okay. So it means that either u1 equal to 0 or s1 equal to 0. So we have to choose either u or s equal to 0. This is called switching condition. So u1 equal to 0 means inactive constraint. u1 equal to 0 means this whole thing is gone. Okay. There is only the original objective function. It means inactive constraint. s1 equal to 0 means active constraint. Okay. So let us use these concepts. Okay, then there's one more condition. The sign of u1 can either be 0 or it can be negative. Okay. So this negative sign of u1 has to do with the rate of change of objective function with unit positive change in constraint boundary. So what is that meaning? We'll see later graphically. Why this u1 can be 0 or negative, and why u1 cannot be positive. Okay, so that reason we'll see later. Okay, so you have to remember these three conditions. That is, all delta L's must be equal to 0. Either u or s must be equal to 0, and u can be 0 or negative. So these are the called KKT conditions or Karush-Kandakar conditions for minimization. Okay. So if you solve these three equations, you will get the values of x star, y star, u star, and s star. And you can check if it is, looking at the value of u and s, we can check if it is active or inactive. Then for maximization, there's another set of rules for KKT conditions, but nobody follows that because people want to follow only one method, that is the minimization method. For maximization, they'll take the negative of the objective function and do the minimization. Okay. So we can look at one simple example in today's class. So using the slack variable method, minimize this objective function subject to this inequality constraint. That is 2 minus x minus y is equal to 0. So what you have to do is that this is equal to g of x. Okay. Okay. So now this is written as g of x is greater than or equal to 0. You have to write it in the less than or equal to 0 form. So it will be minus 2 plus x plus y is less than or equal to 0. So that is the same thing here. Okay. The same thing is shown here. Okay. Plus s squared slack variable equal to 0. Okay. Okay. So this is the Lagrangian for inequality constraint. So here you have original objective function u, the term u for inequality constraint instead of v or nu. Then this is our h of xy plus s squared. So this is the Lagrangian for inequality constraint. Okay. Okay, so this is a partial L by partial x is equal to 0. That is this thing. then this is partial L by partial y is equal to 0. Then this is partial L by partial u is equal to 0. Then this is partial L by partial s is equal to 0. Okay, so we have 4 equations. So this is the switching condition. Okay, u is the switching condition. You have to always start with switching condition. Okay, switching condition. So either u equal to 0 or s equal to 0. You have to try both options and see which gives the correct answer, which does not violate the constraints. Okay. So the u equal to 0 means constraint is totally inactive. S equal to 0 means constraint is active. So these are the only 2 options. Okay, so first let us put u equal to 0. Okay, if you put u equal to 0, if you put u equal to 0, then u is equal to 0, then you get x is equal to 1.5, y is equal to 1.5, then so this is 3, okay? 3 minus 2 plus s squared equal to 0. So s squared equal to minus 1. So this is a constraint violation. Okay, we already studied that negative value of s squared is constraint violation. So this solution is not acceptable. Okay, so this solution is not acceptable because you get s squared equal to minus 1. So next you put s is equal to 0 here. Okay, s is equal to 0. Okay. Okay, so s is equal to 0 means this is going. Okay, and okay, this is gone anyway. Okay, then you have to solve these 3 equations. Okay, in x, y, and u. You have to solve these 3 equations, and the answer is given here. Okay, x star, y star 1, 1. Okay, and u star equal to minus 1. So negative value of u is okay because, as we said earlier, it matches the rate of change of objective function with respect to unit change in constraint boundary. So negative value of u is okay, and this x star y star is also satisfying the constraint. Okay, so correct answer is this: s is equal to 0. So this is the switching conditions. Switching conditions. Okay. So we have active constraint. Okay, I think we can stop here, and the next class we'll do some bigger problems with this. So for the exam, one question will come to use this Lagrange method to solve some inequality constraint. So stop recording, then take attendance.
Ikaw mo.